So let's try to do a diffuser problem, but before we start, I think we should have a couple of equations with us, like the one that said we use this one for sink and sources. I'll probably do a problem around sink and sources also. I will have our mass rate or flow rate, depends what you want to call it, all over 2 pi r. 2 pi r is literally our radius, so we're looking at around the circumference. If this is a source and flow is coming out like that, we're looking at how much flow is getting out of that source. So this is a very beautiful resource that we need. Then we need Bernoulli's. I think Bernoulli says something that really beautiful. Bernoulli said the pressure in should equals to plus 1 over 2 density v squared should equals to the same thing as you go to the other side. So let me say should be constant, right? Because it could be in and out, or maybe in plus another 3 out if there are more out exits and all that. So the question, let me read before. It's a 2D diffuser, 20 degrees radial flow from the source. So it's the same thing. We use this one for sources. Then we have V. This V, I think it's a V. That's this thing goes in here with determine the expression for pressure current along the diffuser wall. So that's, they want us to find pressure gradient. Okay, fine. So in here, okay, this velocity be velocity r to be specific. From here we could just try to, what if we differentiate everything here? I don't know, maybe people might not like this, but it makes things easy for me. Just differentiate everything in here. And also these are partials. Okay, that's means of p. So exactly that's what we like. That's what we want to find. Plus 1 over 2, it's a constant. Density is a constant, considering it's incompressible, so I assume it's incompressible. Then dr of vr squared. Then if I differentiate a constant, I'm going to get a 0. So I'm building this from your Bernoulli's equation. So from now on, I can say my partial with respect, this is my r, I just don't have a good handwriting. R is equals to negative 1 all over 2. This one is like that. And if I'm trying to differentiate velocity radial, which is squared, I'm going, this is more of like a chain rule. I'm differentiating this function and I have to differentiate what is inside it. So if I differentiate, so the outside function is this, right? Then if I differentiate this, I'll get 2 whatever is inside, right? And then what is inside differentiated will give me a dvr all over dr. This thing should also equals to a constant, it's equals to 0. I already used 0, so I'm ready. Okay, fine. So I hope I haven't confused anything so far, but it looks like I can easily cancel those ones, right? I can cancel this 2. Then if that's the case, I'll have partial of p, that's what we're interested in, radially, negative 5. And then vr is that m2 pi r Then if I try to differentiate that, let me do dr of m 2 pi r on the side, and then this is a constant, m 2 pi r are constant. And if I differentiate this, it's going to get me a negative and a 1 over r squared. Okay, cool. This is what we get. We can now come back, plug it in here. We'll have minus m all over 2 pi r squared. That look really beautiful. Okay, this negative will cancel each other. We don't need it, and they will go away. That m will get a squared. This will become 4. Pi will also be squared, and r will be some power. So this is your gradient. So I brought back my question so that I can easily maybe reference what I'm talking about here. So because we have all the values here, we can actually solve for what is our m. We said VR is supposed to be m all over 2 pi. I want to substitute everything there, pi r. Then m, we don't know. We know v, that's on an entry. I think they told us somewhere here. You can notice. Okay, cool. Then v, I said it was 20. I'm not using units. We don't know m, but we know 2 pi, and that this one is recorded on the entry. That means r was 2. Then from here we can solve this become what do you call this? This become 4 times 20 become 80. Then I can say m is equals to 80 pi. We now have m here, so it's looking good. We now have m here. R is a variable that you want to change. This one is 1000. If this is water, water, they did tell us this is water here. Hope you can see. Then let's try to finish up. I think we can now get the exact value if possible. This is 1000. This is 80 pi. Now I have to square it all over 4 pi. I think this thing was supposed to be squared. The power is supposed to be squared because there are 2 of them there. Okay, and r is supposed to go to power 3. So this is going to be our gradient. So I don't know if you compute that. Let me try to put my... Okay, let's just say if you compute that, you get some number, and that number should be some number on top divided by r power 3. So because you don't know the r that you're interested in. Then the next question, they'll say find the pressure rise. This one, I think they meant to say the delta P. So we'll start from Bernoulli's again. I think it's, let me call it entry plus half v squared, and what else? This should be a constant. P at exit, I'm going to call exit O, plus 1 over 2 density like that. These are R. We already know here we have 20. If I take this to the other side, I'll get my delta P, of which I'm interested in. Then I'll have this one will be 1 over 2. This is a common factor, and then here I'll have V out, okay, minus V entry. All these V's are squared. Then 1 over 2. This one I assume it's the 1000. If this is water. V out I don't know, but I can compute minus 20 squared. Then V out I can still use that VR is equals to m. Did it give us m? Oh, I got m to be 80 pi all over. There's 2 pi r, right, for circumference, and my r on the exit is 7. Literally it's from here to there, so my r is 7. Here's the number there. Okay, so I can put 7 there. Then I hopefully can get my v, and whatever v that I get, the value that I get here, I plug in here. Then I have only constant values, then I can get it here.